it'll attach and share everything properly. That's been my experience. I mean, that's probably not a good experience.
There we go. We're rocking. You see your island, Aaron. There we go.
See you, Aaron. That's great. Hello.
Can we not hear him talking?
No, Aaron is muted.
Joel, you have to unmute him. There you go. There he is. I recognize that laugh.
Trolling you guys.
Look, I'm just trying to give like the traditional Zoom experience here. Okay. Hello, everybody. Hello, Aaron. I hear you all saying hello, Aaron.
Hello, Aaron.
Hi.
Hello.
Hey.
Happy Wednesday, everyone. At least I think it is Wednesday. It has been a long, recent amount of time. My name is Aaron. It is nice to meet you all. I'm also known on the internet as Tender Love. And if you don't recognize me over this Zoom, this is my icon online. This is what I look like online. You can see this is my real life self. Actually, this is my long hair. This is my I need a haircut self. But that's gonna have to wait for a little while. A little bit of exciting news about me is that I got a new job. I used to work at a tiny startup, and now I've moved to a different tiny startup. And the first thing I did was find their keynote slides and ruin them. So you can see here I'm not on brand. I am aiming to give a 1-hour presentation, but to be honest, like I have never ever actually given this talk before, so I'm not sure if I'm either going to go way over or way under. But the point is here that I am extremely nervous about it. And I can't even see my presenter notes, which is making me even more nervous. There we go. So what I'd like to do is, since this isn't a traditional talk, like we're all on a Zoom here, and these are not like normal times. What I'd like to do is kind of make it more interactive. So if you have any questions while I'm giving this presentation, like please say so we can talk about it. My goal here is actually to make sure that everybody can come away learning something new. And that's at all different levels. So please feel free to ask me anything. I'm really happy to answer any questions at all. So anything along the way, please feel free to ask. So today I'm going to be talking a bit about instance variables, which is a kind of a strange topic. I mean, usually I talk about, I don't know, other performance things or like garbage collector details or things like that. But today I want to talk about instance variables, and I decided to call this talk Don't At Me.
So good. So good.
That's it. We're done. Okay. I did.
Wow. It's a mic drop. We're done.
We saw Gorby and he made a joke.
I made a joke. I did it. Oh, I can't see the chat. Hold on a sec. And I can't get the thing. Okay. If you have questions, please unmute yourself and say, hey, Aaron, I have a question, because I can't pull up the chat in this thing.
Is there a raise hand thing in here? I think maybe that would be helpful. I've seen that.
Oh, I see that. Okay.
There's also a go faster button. What does that do?
Turbo.
Hold on. I'm going to stop this thing for a sec. There's a more button in here. There's a chat. Okay. This is cool. I have to quit the presentation to pull up the chat. Okay. Oh yeah. So I used to work for GitHub, and now I work for Shopify. And at Shopify, we use Google Meet. At GitHub, we use Zoom, and like I have to admit, I'm pretty happy to be using Zoom today. I am not a huge fan of Google Meet. It is very hard to use, and there is no like. One thing I really miss about Zoom is having the virtual backgrounds. Like I can do, you know, let's do this here. So for example, I can have a virtual background of just me. You can't do that. You can't do that in Google Meet. And I have to admit, like, so I've cleaned, like, we're gonna do this. We're having a like a group meeting here in everybody's homes, and like whenever I was in meetings at work at GitHub, I would always put on a virtual background because my office is kind of a mess. Now Google Meet does not have that, so I had to clean up my office before I met with anybody at work. So you can see here, I'm going to show you a little pro tip here. This is my like fun desk, which folds down here, and you can see that it contains a mess. Anyway, yes, I thought I would share that. Okay, so don't at me. Now I'm going to make a joke here, and it's very Northwest specific, so I apologize. It's not going to make any sense to any of you, but if anyone from the Northwest watches this later, they'll be like, wow, that was very funny, Aaron. Oh, I don't want that. So we're going to talk about IVARs. The good news about IVARs in Ruby is that they won't cost you a lot of clams. This doesn't make, I know, like, this does not make sense to any of you. That's fine. I was actually going to try and find, like, I was looking through Wikipedia, looking for local Boulder businesses to see if I could somehow make a pun with instance variables and Boulder businesses, but it did not, I couldn't find anything good. So yeah, I found like, I was like, oh, there's SendGrid, but that's like, I don't know how I would do that. I was thinking about making like a grid of calling send in Ruby or something like that, but that doesn't have anything to do with instance variables. So anyway, sorry, you're getting a Northwest joke here. Oh, I forgot to mention, I live in Seattle. That is the connection. I'm not just making like random Northwest jokes. All right, so first let's talk about how instance variables are stored. We're going to talk about how instance variables are stored in Ruby, including the data structures involved and how these data structures relate to each other. So we have data and structures, and these data structures point to each other. So then we're going to talk about this storage, the way that instance variables are stored. It relates to the performance of instance variables. So we're going to talk about instance variable performance. And we're also going to talk a little bit about inline caches as well. But before we get into the like fine details of these topics, I want to show you a very weird benchmark. So here is the weird benchmark. And basically, what this benchmark does is it defines a whole bunch of instance variables. It defines them from A to Z. So first it goes forward, it defines an instance variable A, then B, then C, then D, et cetera, until it hits to double Z. And then it defines instance variables backwards from ZZ all the way back to A. So you can see we're just, evaluating some code here that we have a go forward method that defines the instance variables forward. And then we have a go backwards method that defines all the instance variables backwards. So if we were to like, expand out what this code looked like, it would look something like this, where we're just saying like, okay, our forward one is like A, B, C, D, E all the way through. And then our reverse method will look like this, where it's just like Z, Z, well, ZX, ZY, all those backwards to A. And if we run this benchmark, we'll see that it looks like this, where the higher numbers are better. So we're measuring iterations per second. So we're measuring how many times can we call this method per second, which means that the higher number is faster. And if we look at the benchmark results, it's actually faster to define our instance variables backwards than it is to define them forwards. And once we get done with this presentation, you will be able to answer the question, why? Why is it that defining them backwards is faster than defining them forwards? And yes, there's absolutely a trick. And at the end of this presentation, I hope that all of you will know the trick. So let's take a look at instance variables. We're going to talk about instance variables. We're not going to talk about class variables. So not these, not the double ats, but we're going to talk about instance variables, which are these, just the single ats. And to talk about this, I want to discuss how we might implement instance variables. How will we implement these? So to implement instance variables, we need to think about the different parts of an instance variable. So let's look at some code again here. Our instance variables, they have 3 different parts. So they have a target, a name, and a value. And our name is just the instance variable name. So in this case, it's Baz. And the value is just the number 10. So whatever value we're assigning to that instance variable. And then we actually have a target too. And it's not very clear what the target is, but the target is self. So it's kind of like how you can call a method, but you don't have to say self dot blah. You can just call the method. So we have this kind of invisible self. We're applying the instance variable to these 2 things. Now, if we wanted to store this, a natural data structure that we might use is a hash, because we have a key, which is our name, and we have a value, which is our value. So this seems like a pretty clear way to store these things. So our first iteration of implementing instance variables might be to use a hash. So if we did that, we'd end up something like this, where we have an instance of the class foo, and it points at hash bar and baz. So we have the key and the value pair there. Now, there's kind of a problem with this implementation. So let's take a look at some code this code is made up, of course, but I hope it is representative of at least some code that we might write. This is my implementation of FizzBuzz. You can see it does not work. It's just some sample code. So in this particular example, we first write, when we initialize the foo instance, we write to the instance variable here. So in our implementation of instance variables, we'll end up with a hash where the key is Baz and the value is 10. Then later on, we might call the Baz method, and we'll read that instance variable. And in that case, we're going to be getting the value back out of the hash table. So this case just reads it. And then down here at the bottom, we're going to really, really read this. So we're doing a lot of reads on this thing, and it just does way too many. So the idea is, we have to do these reads so many times. We read a lot. We actually read a lot more than we write. And the question is, well, how expensive is it for us to calculate the hash of Baz? Because every time we do a read on the instance variable, we have to go look it up by that name. We have to say, hey, what's the hash of the string Baz, and then what value is it holding? So we know one thing about our code, and that's typically that we're doing a lot more reading than we're doing writing. So we'll read instance variables a lot more frequently than we actually write to them. So our reads outweigh our writes. And unfortunately, using a hash, calculating that hash value, is just going to take way too long. We'd like to do something a bit faster than calculating hash values, but what would be faster than a hash? And the clear answer here is using an array. An array would be way faster than using a hash, and we can actually prove this. So let's write a little benchmark here. So we have a hash that's our instance variable implementation, and then we have an array here, which is our other instance variable implementation. So we'll say if we run this benchmark, it's going to be very clear who the winner is here, but doing array reads is much faster than doing hash reads. Like 46, it's 1.46 times slower. It's much slower to do hash reads than an array read. So it would be nice if we could just implement these instance variables using an array. But the question is, like, if we look at this implementation here, we see like, oh, we have to know the index of the instance variable in that array. Like, how do we get that value? Like, what is this index? Like, how can we figure out the index of the value Baz? Where do we get that? Well, the answer is, instead of just using an array, we'll actually use a hash and an array. We'll use both of these. So to design this system, what we'll do is we'll say, okay, we're going to have a class foo, that's our normal class, and we'll have an instance of foo. And our class foo will point at a table. The hash table will just be the Baz, the name Baz, with the index 0. So our hash will be the name along with the array index. And then in the instance of foo, we'll just store an array, and that array will have each of the values for the instance variables. So another issue that we have to deal with is we'll have to deal with table expansion. So let's say for example, we have an object with 2 instance variables that looks like this. So our data structures for this case would look something like this, where we have a class. The class foo points at a hash, and of course, the hash table has 2 entries in it, Baz and Buzz with index 0 and 1. And then our instance variable array, it has 2 entries. At 0, we have the value 10, and then at place 1, we have the value hello. So let's walk through this code actually in slow motion. So we're going to do this in slow motion. And I'm going to pause to see if anybody has questions. Please have questions.
I wanted you to walk through how a read would happen, but it seems like that's what we're going to do. Is that what the next?
Yes.
Okay.
Yes,
cool.
exactly. We're going to do a read. So we're going to do a slow. Oh, no, we're not going to do a read. We're going to do a write. We'll talk about reads. So let's do a write, and then we'll do a read. So let's do a write first. So this very slow motion. Actually, we'll stop right after the slow motion thing to talk about it a little bit. So the first thing we'll do is we'll define a class. So this code executes, and we've defined the class foo by the time we get to the bottom here. Then we're going to execute foo.new. And when that happens, we get an instance of foo that points at the class. Now, this will go into the initialize method. So we go into the, like, new goes up into the initialize method. And then we define the instance variable Baz. And that will create a hash on the class, and it'll insert Baz at place 0. And then in the instance variable array, we'll store the value 10. Then, of course, we move on to Buzz. Buzz will store the instance variable as well, or Buzz will store a new entry in the hash with place 1, and then we store the string hello in the instance variable array. Next, we'll go on to, if we do this again, like a second time, this hash is actually persistent between calls, so the hash lives on to the next call, and we'll say, okay, we have an instance of foo. The instance of foo points at Baz. Well, the instance of foo points at the class. The class contains the hash table. The hash table points at an array, and then we insert these values into each position in the array. So an interesting thing is that, as execution starts, like as we execute this, the important thing is the very first thing that's seen. So the first time we see an instance variable, that determines the position that it's in the array as well as the hash. And this is probably kind of confusing, but I'm going to show you an example, which may or may not clear it up. But this is the example. Let's say we have an initialize method that says like, okay, I'm going to execute the top half of this a random number of times and the bottom half a random number of times. This is some weird code you would probably not like. Don't do this in production, please. So if we do this randomly, let's say the very first branch, that top one, let's say it runs first. If it runs first, then Baz is going to get index 0, and then Buzz will get index 1. And this is the very first time. So even if we run this multiple times, it's going to stick with whichever branch ran first. Now, if the else branch ran first, then Buzz will be the first one, and Baz will be the second one. And you'll notice here a limitation of keynote. If you look at the, I guess I can't really point at my slides, but if you look at the second table there, it says like hash -1. You can't have two tables with the same name in keynote, I have learned. How much time do we have? I want to do a thing that is not part of my slides.
I don't think there's any real time limit here. So.
All right, does anyone mind if we pop out to a terminal real quick? We'll do some live coding.
Go for
Do
it.
it.
Okay, let's do it. So this is kind of cool. Let me get a terminal here. Bring it over. Let's make the font bigger. Can everybody see this okay? Make it bigger? Okay.
That's pretty good.
Okay, so let's say we have x.rb, let's not do x.rb. Let's do b.rb. So we were talking about how the class stores this hash table, right? The class is the one that actually stores the hash table of instance variable names to instance variable. Jeremy, I have so many x.rbs everywhere, it's like really bad. So the class actually stores this map of instance variable names to positions. So what we can do here, we're gonna actually see this happen in real life. So let's say we have like class foo def initialize. Spell that correct? No, I didn't spell that correctly. Initialized. Okay, and we'll do like foo equals bar, and then we'll do bar equals Baz, like this. Now we're gonna do something kind of weird here. Let's say let's look at the how much memory this class takes. Like, what is the size of this class in memory? We can do this with object space. So we can say like p ob space or object space dot mem size of foo. So let's try this out and see what the size is. So we'll do Ruby b.rb. Oh, we probably need to require ob space. So we'll run that. Okay, it's 536. All right, that's the size. So let's print it out, but then let's do like foo.new and then print it out again. We'll do before, and then we'll do after. So foo.new, we just ran foo.new, and then we're gonna run this again. So we can see here, let me pull up the code. Oops, that's not what I want. /t? No. Okay, there we go. So we got our code on the bottom here. We're gonna look at the mem size of the foo class before we instantiated it, and then we're gonna look at the mem size of the foo class after we instantiated it. So if we run this b.rb, we'll see that before we called foo.new, it was smaller. And then after we called foo.new, the class actually got larger. And that's because we're storing that hash table of instance variables on the class itself. And if we call foo.new again and say like after 2, we'll see that the values should remain the same. Is my keyboard super loud?
Wait, can I
hope
ask
so.
you a question?
Yeah, yes, please.
So between the before and after it increases, why does it not increase again between the after and the after 2? Is that something that I just missed while you were going through that?
Sure. It's a great question. So the question is why does it stay the same between the second 2 values, right?
Yeah, that's my question.
Yeah. How come it didn't grow when we called foo.new again? The reason is because we're maintaining that same table size. So the table of name to index stays on the class and doesn't change in size. So it's only like, imagine it as a hash table where the keys are just foo and bar here. It's going to be, the keys are the names of the instance variables, and the values are the offset in the table. So
Okay. So so foo.new, like, let's just say that we have F1 and F2 are the actual instances.
yeah,
Because they have the same indices for where these variables live, the class maintains the same size through multiple iterations. But when you say F1 or F2, it's the same it's the same index.
Yep. Yes. That is exactly it. Yep. And we can do like, we can actually increase this size too. It's dynamic. So let's add another method and see if we can get it to grow. I'm not 100% sure we'll be able to make it grow, but let's try. I mean, we can make it grow, but it might take a little effort. So let's do it. Let's try it out here. We'll do def add more ivars. Let's just do like A equals 1, B equals 2. Let's try this. We'll try this. I'm not sure if it'll work. So actually, I'm gonna exit this. Just exit that. So we'll call foo.new here. So this one will get bigger. Let's call foo.new.add more ivars, and then this one should be bigger. Let's try. How come I cannot control Z? Oh, geez. There we go. Yep. Okay. So we were able to make it. We were able to make it grow because we added more on that second call. Okay. So we know foo stores a map of name to index. All right. So let's head back into the slides. Okay, so order impacts the index. Order impacts this index, and the index will stay the same. The index hash stays the same depending on the first instance variables that are seen. So even if we execute the top branch, the map will contain Baz pointing to 0 and Buzz pointing to 1. Even if we execute the bottom branch later, those two will remain the same. And likewise, if we executed the else branch first, Buzz will point at 0, Baz will point at 1. Even if we execute that top branch later on, the indexes will stay the same. So let's do one more experiment here. We'll have class foo, we have an if and an else, and we can control which branch executes based on the value that we pass in to initialize. So again, first we go through and define the class foo. Then we'll call new, and this will create an instance of foo. We'll pass in true. So the first thing that happens is it'll write a is 0 to the hash, and it'll set the value hello. B will write b is 1, and then we'll say how. C is 2, and then that'll point to R, and then D is 3, and that'll point to U. Then for our second call, we call foo.new again, and it creates an instance of foo that points to the class foo. And it'll go through here and it'll create these the same array, but we don't expand the hash or do anything with the instance variable index hash at all. So we keep expanding these. Now, an interesting thing to note is that each time we set an instance variable, we actually have to grow this array. So this array here that's showing on the right-hand side, it has to get longer and longer, okay? So it gets bigger and bigger, and that actually costs us. We have to do a realloc. We have to say, hey, operating system, give me more memory to store these instance variables, and we have to do that each time we expand this array. So this will actually take a few, is that text showing up there? No, this will take 1 malloc and 3 reallocs. So we say we malloc at the beginning to get that very first chunk of the array, and then we realloc 3 times in order to expand the array down, right? Because we have to keep making that array larger for each instance variable that we add. Now, let's contrast that with if we called foo and we passed in false to initialize. So we'll pass in false this time, and we'll get an instance of foo. False will come in here, and instead of executing that first block, we'll execute the else block. And you'll see here in the else block, we're actually defining the instance variables backwards. So in this case, we'll say, okay, D, the index of D is 3. So we have to store a value at the 3rd position in the array. So we have to expand the array down so that it's large enough in order to fit index 3. So once we've expanded the array down, we insert that value U into index 3, and then we'll keep moving on. We'll say, okay, C is now at 2, B is now at 1, and then A is at 0, and now we've filled in our instance variables. So in this case, we've only done 1 malloc because we had to malloc the array large enough to hold all the instance variables, and 0 reallocs. Any questions?
So I actually wrote an article. I've watched a lot of your videos. I wrote an article about the garbage collector. And so I'm curious, is this going into is this managed by the C section of the Ruby heap, or is it managed by the Ruby section of the Ruby heap?
That's a very good question. It's managed by both of them. So I'm taking some, like, let's get into some dirty details here. I'm taking some huge liberties, massive liberties with these slides. So actually what happens is the very first allocation, like the first 3 instance variables are actually stored inside of the object itself. So we don't actually allocate anything in that case. Those are managed by Ruby's garbage collector. Anything beyond 3 is done outside of the GC and has to be malloced. What's beyond that, it doesn't actually do a realloc for every single insertion. It actually reallocs like 2x the number it needs. So let's do another experiment. Since I seem to be doing okay at live coding. So let's do this. I'm going to show you an example. So we were talking about how this array has to expand each time we insert a value. Actually, I'm sorry, did that answer your question?
I think so. I think that the short answer is there's a lot of stuff going on that you're simplifying because you're giving a talk over Zoom to people with varying experience levels, which still totally makes sense. So yes, my curiosity is satisfied. Thank you.
Well, it's managed by the GC in some cases. The object, when the object gets freed, it may actually have to call the free system call in order to free the instance variable array. But the answer is it depends on how many instance variables there are stored in the object itself. So to drive this home, I'm going to show you an example, and let's see. We're going to have my cat is doing something. Okay. Let's have an object here, foo, and we're going to just do foo.new. And weird. Somebody is calling me. I don't get phone calls, so I don't know why someone would call me. All right. Let's do p object space. Like, I think the only people who ever call me are my parents. I don't. All right, and it's not them, so I'm not answering. Yes, definitely spam to verify my business. Mem size of, so let's look at the size of this object itself. And I want to do one thing. Let's make sure we're not on Ruby 2.8 because these slides change in Ruby 2.8, and I will talk about that too. So let's do this. All right, so if we look at b.rb, it's size 40, okay? Now if we add an instance variable at a equals 1, let's add 3 instance variables. And then let's look at the size. So if we run this, it's still 40, all right? Now, if we add our 4th instance variable, let's see what the size is. If you run that, you'll see that now all of a sudden the size is 80. And this is because this is the point where we actually have to start allocating that array from the system. We have to start asking the system for memory. And I showed you in the slides that each time we do an insert into that, we're actually expanding the array, but that's not actually true. If we did that, it would be way too expensive. So what actually happens is if we add another instance variable, print it out here, so we'll add e, we'll see that the size doesn't change. It stays at 80. And that's because what actually happens is when we hit a certain number, it'll allocate more headroom. So it just doubles the amount of room that it uses each time. And this can actually cause wasted space in the first allocation, but I forgot where those are, or I forgot where that, I don't have a good way to demonstrate that to you live. I'd have to do some messing around, but there is a way for this to waste space.
Hey, Aaron.
Anyway.
Size here, it's 80 what? Is that bytes or pages or something else?
Bytes, 80 bytes. Yep.
Nice.
And we can do like, actually, let's do, this is, I'm not writing very good Ruby code here, okay. Please. So we'll define a whole bunch of instance variables. So we started off at 40, we were 40 here. Let's just do that here. Let's see what the size is here. So it's pretty large. Now an interesting thing is, let's do it a second time, and I bet the numbers are different. So you see the second instance, it started out at 40 like the first one did, but then when we got to the very end, it's actually smaller. So does that seem reasonable to everybody?
But why?
No.
It seems completely counterintuitive to me too. But let's talk about why. Let's do a third one. We'll do a third one. The third one will be the same as the second one.
Is it
Okay.
because it's so? Can you go back to the code? Sorry.
Yeah.
Is it because symbols only exist once in the runtime? So the second, like the first time you run the mem size of, the symbol is not there, but then you do this eval and then it is there, and then the third time you run it, like it's still there. Is that what's happening?
No. We could actually do integers if we wanted to. Let's change it to a number. Let's just do 1. We
Okay,
do 1 and run.
Then I'm very confused.
Yeah.
I would
It's
suspect
just
impacting GC here.
So just figure out the first time around what headroom it actually needs for the second time.
Yeah, so the first time, basically what's happening is each time we have to expand this hash, so every time we insert into the hash, we're expanding this array, we're expanding the hash, and we're also expanding the array, right? And what we do is, or what Ruby does is it says like, okay, oh, I have to expand the array, so I'm just gonna double the size, okay? So it just keeps doubling the size. But the next time we allocate it, we never had to expand that hash. That hash was the same size the next time around. So Ruby only allocates the size of that hash, right? So it's gonna be like, if we have to expand the hash, it adds headroom. If it doesn't expand the hash, then it doesn't leave any headroom. So the first time we do it, it's gonna be larger, but every subsequent allocation will be only the size of that hash. What do you call a phobia of the third variable? I don't know. The fourth dimension? Okay, does that make sense to everybody? Expanding hashes? Hopefully, okay. All right, let's go back to the slides. Okay, what do we do here? Yes, we did that. Cool. Expanding arrays. Great. Okay, so knowing what we know now, if we go back to our let's go back to our weird benchmark. Our weird benchmark allocates all the instance variables, or sets all the instance variables forward, and then it sets all the instance variables backwards. So we saw that as we go forward, we have to expand the array, but as we go backwards, we don't have to do that. So in this case, going forwards, we'll do 1 malloc plus many reallocs in order to expand that array, where our second one, going backwards, we'll do 1 allocation because it's starting at the very bottom of the list and filling it back into the top. So that is why defining instance variables backwards is faster. Are you all convinced?
Wait. Can you say that again? So you have one, when you're going forward, you have one, you're mallocing, maybe walk through it again.
Yeah, sure. So here is a short example. So this is essentially the same thing we were doing in the weird benchmark, but on a smaller scale. So in the first case, let's rewind to the first case. So in the first case, we'll define foo, the class. We'll walk through it. We'll create a new instance of foo, and we pass in true. True will walk through the true branch. And our very first time that we allocate, we have to create this hash table, which we do, but we also have to expand the instance variable array. But this isn't where our bottleneck is. Our bottleneck is on the second allocation, because we only create that hash table once, like we were talking about. That only ever happens once. Now, the second time we allocate foo, it'll go into initialize. We'll create an instance of foo. It'll go into initialize, and then we'll have to do 1 malloc to create the array that stores instance variables. But each time we add a new instance variable, it has to expand that array a little bit,
right,
in order to fit the new one. Now, if we contrast this, because we have to store A at position 0 and then B at position 1, et cetera, et cetera. Now, if we contrast this with the backwards implementation where we're saying, oh, we're going to go into the else block. So that's one malloc and three alloc, sorry. In this case, when we go into the else block, D is stored at position 3. So we have to expand the array in order to have a position 3 to store D at.
Is that because you've already ran through
Oh.
the true part?
Yeah.
Okay.
So the hash table stays constant. The hash table always contains name to index. And that third time when we call foo.new, it has to set the, hold on, my mind is going blank here. D has to go to position 3. So we have to expand the array large enough such that position 3 actually exists and we can store something in there.
Okay, I think I'm following now, actually.
Okay.
So then on the next one, the preceding elements of the array already exist because you had to expand it.
Yeah, exactly.
Okay, all right.
Exactly, yes. So now C, when we insert C, that position already exists, so we just store a variable value there. We don't have to expand the array anymore, and we can keep doing this. And actually, yes.
I have a question. If the sequence that you called foo.new started with the false case, would the hash table be defined with DCBA in order, or is the position of those things in the hash table the order in which they appear as lines in the class?
No, it's not anything to do with lines in the source. It's with what order they were first executed by the VM.
Okay. Thank you.
So we can, yeah, you're welcome. So one thing we can see here, let's try another experiment. I'm not sure if we can do that. Let's try. We're gonna try. I might be able to demonstrate the array growing in size. So we'll give it a whirl. Like I said, the behavior since it's doubling sizes, I may not be able to come up with numbers that will show it exactly. I would have to fiddle around with the different numbers, but let's do an experiment. So we're gonna do, let's create a method that defines up to ZZ. So we'll just define all of those. And let's do another one that's just, up to, yeah, AA, I guess. No, A up to AA. And then let's go, how can I do this? What I want to try to do is define half of the instance variables and then look at the mem size and then define the other half of the instance variables. And then we can see, then we're able to observe that the array increases in size. So now that I've said that out loud, let's write two methods that do that.
You could do AA to MM and then MM to ZZ. That would give you half to half.
Like that.
Well, the first one's gonna have 26 extra, but you could do AA to MM, and then
This does A to ZZ though. Help. Jeremy, tell me what to type.
up to MM and make it be AA to MM,
Okay.
and then do up to ZZ, which would be MM to ZZ. Wouldn't that do it?
Okay.
And then that should do half and half.
Okay. So let's do this. We'll do so this one's going to define all of them up to MM. So we're going to use full in order to fill out that hash table. Paul, that is correct. Yes. It's nothing to do with alphabetical. It's just doing half at a time. It's the order in which they're seen.
Yeah, that was a follow-up to my earlier question about what happens if you swap the order of them in the benchmark.
Yep.
Okay.
Actually, I have a great idea. I have a really great idea. That'll be even better. This will show it very well. Okay, so we're going to do all of them. We'll just do A to ZZ. Sorry, I hope this is okay. I'm sorry we're doing this like random stuff. I did want to make this more
Keep it up. Keep it up.
thank you. I did want to make this a bit more like interactive, so I hope we're like doing it.
This is great. I love it.
Okay, so we're going to do one that fills in. We're going to do one that fills in everything. So let's create a keyword. How much? We'll do like if how much equals all or everything. We'll fill in everything. Oops. Okay, we're gonna add another method that's like def just a. Let's do another one that's just. Okay. So we have one method that just does a, and one method that just does ZZ. And then we have one method that does a all the way to ZZ. So we'll do new and we'll say everything. Actually, I'm going to split screen so I can read this. I can't remember how much. Okay. So this will be everything. This will be just a. So we'll print out the mem size of everything. So we'll print out the object space of everything. Actually, I'm going to do that first. We'll just print out everything and take a look. So it's 5704. If we fill in all the instance variables, it's 5704. Let's do another one that's just a. And we're going to print out the size before we call anything, and then we're going to do just a dot just a. So just a will define the a instance variable, and we'll print out the size of that one. Following along here? So this one should get just the head of the list. It's not going to get the whole thing. We see that it's size 40 if we just do just a. Now let's do just Z. Or just ZZ. So this one, it's only going to define the ZZ instance variable. Oops. Did I not spell just ZZ correctly?
Your object name is just A instead of just ZZ.
Oops. Oh, geez.
Down 2 lines.
Yeah, you flip that around.
So our first one fills out the hash table. This one does nothing. And if we run this, we see when we define just ZZ, the size is very large. And that's because it allocated the entire array. But if we do just ZZ.instance, we see it only contains the ZZ instance variable. Is everyone adequately confused?
Mildly. Could we look at the code like that you defined in the class now that you ran through it?
Yeah.
That always helps.
Actually, I'll make this, let me make the font a little bit smaller so I can fit more on the screen here. Let me know if it's too, like, I don't want to go too small. If it's too small, let me know.
No, that looks fine to me.
Actually, you know what might make this a little bit easier? Let's do nothing and initialized.
Yeah, just seeing it all is helpful for sure.
So this one will fill out that entire hash table. This does nothing here. Then we define just ZZ and we look at the instance variable. You can see that it's large even though we only have one instance variable. And if we compare that to just running just A, so let's change this to just A, we see the size is 40 and it only has one instance variable as well.
So if you were to define a method that was just Z, would it be, and you were to call all the instance variables on Z, would that then be everything from Z to ZZ, and nothing between A and Y? And then also the mem size would be somewhere in the range between that 40 and 5,000 bytes.
Oh, you're saying if I chose a letter that was in the middle.
Right.
Yeah, it will be. Let's do one in the middle.
Okay.
So let's do like
AA or Z would be like right in the middle, right?
just do AA. Oh, geez. All right, so we'll do just AA and check the size. See, it's 304. So wherever it is, it'll expand. It has to expand the array to meet that size. That makes sense?
If you do it, the little one and then the big one, you know, the just AA and then call just ZZ, do you get the slightly larger 5,000 byte one or the slightly smaller 5,000 byte one?
Tell me what to type.
Do line 5 right now. Yeah, and right after this, do just ZZ. And what's the size? I'm just
Can I expand it all the way? Actually, hold on. Let me go back to
500, the 5656 or the 5800 one we had before. Okay. All right.
It'll bring it all the way out. Now, I've made a change. So the reason I wanted to show you this on Ruby 2.7 is I've made a change in Ruby 2.8 that makes this behavior, like, I think, a lot simpler. If we run with Ruby 2.8, is not released yet and might be Ruby 3. If we run with Ruby 2.8, it'll always be the same size. It'll be the maximum size. So if we call just AA, it'll be 5656. If we call ZZ, it'll be 5656. Yes. Dan, yes, the answer is there is no more reallocs. Yes. All right. Let's keep going. Okay. We did this. Yay, we did this. Okay, so now we know why going backwards is faster than going forwards. It's because we only do one realloc. We don't have to keep growing that array larger and larger. Okay, so caveats. Let's talk about some caveats. Ruby doesn't actually do one realloc for every IVAR, as we talked about already. It actually increases the size by 2x. So each expansion, you don't need to worry about these expansions so much. It's not actually a big deal inside of, I mean, it's not a very big deal. Also on top of that, there's a thing inside of Ruby 2.7 called the transient heap. The transient heap is, I'm not gonna get into it into this presentation, but we can talk about it later if you want. Like I said, anything is fine. This is just like a way to optimize memory allocation in Ruby 2.7. Ruby 2.8 eliminates array expansions altogether mostly, so that's why we saw these numbers were essentially the same on Ruby 2.8. It's just one rule. So let's continue a bit with instance variable performance. We said earlier, like we talked about using a hash implementation, and we decided that using a hash is too slow because we don't want to calculate the key every single time. We decided that we should use a hash and an array because array lookups are faster. We decided we would do both of these. But now we're going to look at instance variable reads. We're going to use both of these, but I want to talk about doing an instance variable read. So let's follow this. Let's step through the execution of this code slowly and try and figure out what's going on when we read an instance variable. So in this case, we'll say, okay, we're going to call what is Baz on foo, and that'll, why can I not see the animations on mine? Come on, there we go. Okay, so we'll call what is Baz, and that's going to read the instance variable Baz. And in order to read that instance variable, first we have to look up the index in the hash. So you say, like, where is this instance variable stored in the array? So it'll go look up in the hash, hey Baz, what is your position? The position is 0. So I see, okay, the position is 0, and we look that up on the class. And now we say, okay, I'm going to go look up position 0 in the array. So it goes and looks up the position in the array. Now, you might notice something a little bit strange here, because like earlier I said to you, oh, we'll use a hash and an array because it'll be faster. But we're just seeing here that, like, well, we said the slow way was to do a hash lookup, but I told you that the fast way was to do a hash lookup and an array lookup. That doesn't really make sense. Why are we doing both of them? Like, we said hash lookups are slow, and here we are doing a hash lookup and an array lookup. So how can we reconcile this difference? So I added some question mark emojis, like, how can we think about this? So the way that we're able to deal with this lookup is that we can actually cache the hash lookup. And these are cached inside of what's called an inline cache. So the slow way is to do a hash lookup every single time. So we do a hash lookup every single time we access an instance variable. Our faster way is, well, we do a hash lookup once, we get the index from that, and then we cache that index, and then every subsequent time we just reuse that index and look up in the array. So what is an inline cache? So I think we need to wind back a little bit and talk about what this is. When we run a Ruby program, the program itself goes through a few different phases. It starts off as text that you've put into your editor, and then Ruby turns that into what's called an abstract syntax tree. And what that is just a tree data structure that represents that program. Then it takes that that tree data structure and converts it into a linked list, which is, we call it IR, but it stands for intermediate representation. All it is just a list. And we do this so that we can perform optimizations on it. So we rearrange chunks inside the list in order to make the program faster. After we do that rearrangement, then we convert the list into bytecode, and the bytecode is what the virtual machine actually executes. So our bytecode is actually just a list of instructions. It's really just a list, and the virtual machine executes all the instructions inside that list. So Ruby's virtual machine is actually a stack-based virtual machine, and we're going to walk through what this is. And when I say Ruby, I mean MRI. I don't mean JRuby or Truffle. They have different virtual machines. MRI's virtual machine is stack-based. JRuby's is not. I'm not sure about Truffle Ruby. If we look at instruction sequences generated from a program, so let's take an example here. We have a sample program, which is 5 plus 3. On the right-hand side, that's what the instruction sequences might look like. They're actually just numbers. If we look at the data, it's just stored as integers. Oh, Daniel.
Hey, my question was similar to Dan's a ways back, and we can get back to it later. I was just curious to know if there is this hash that exists with the values. Where does it live, and can we access it as an attribute of a class? But if that's too complex and it's living in some weird buffer thing, then we can skip it and come back to it later.
The answer is it's stored on the class, so we can see, like, actually let's jump back into our sample program here. This ought to be fun, like, just for a laugh. We'll see, like, let's fill in the whole thing. So we'll print out the size. That hash map is stored on the class object itself. So if we print out the size of, oops, I want that. Oh, I copied way too much stuff. So let's print out the size of foo. Now we can't get access to that hash map. There's no way to get access to it. I mean, there is a way, but it's not nice. And it's not public at all. It's very, like, off the beaten path. But we can see the effect of it. So if we look at the size of foo, the memsize function call takes into account the size of that hash. So we can see the size of a class before the hash is created, and then we can see the size of the hash, or we can see the size of the class after, and then we can know that the hash has been created and increased in size. So actually, let's take a look at this. Let's do x equals this. So we'll fill it in here. So this creates the hash table right here and makes it very large. Then we'll compare afterwards. So before we created that very large hash table, the class was about 600 bytes. After, it's nearly 30K. So we can say that hash table is probably around 28K. So we can't get access to it, but we can know that it's there and it consumes space.
Got it. Thank you.
Yeah, you're welcome. Okay, all right. So say we have a program here that's just 5 plus 3, and we convert that into instruction sequences. They'll look something like this, though, as I was saying, they're just stored as integers, not symbols and stuff. I just translated them into Ruby, so it makes more sense looking at just reading. Ruby is much easier to consume than into a list of integers. All right, so each of these instructions, so each entry in this array is a different instruction. Each instruction has an operand, and in the first case, the operand is 5. And then they also have a name, and the push is the name of the instruction. So the way the VM works is it actually just goes through and executes each of these instructions in the list. So in this case, what will happen is we'll say, the VM will say, okay, I'm going to push 5 onto a stack. So it pushes on 5. Then it pushes 3 onto the stack too. And then it executes the add instruction. And that add instruction, all it does is it pops 2 off, adds them together, and then pushes the value that it came up with back on. So we'll execute add, it pops these 2 off, and then pushes 8 back onto the stack. Now we can walk through this process again in a similar fashion with instance variables like this. So we'll say, okay, our sample program assigns the value 10 to an instance variable, and then we'll print out the value of the instance variable. So on the left is our code, and on the right is the instruction sequences that we come up with. And when these execute, we'll just push 10 onto the stack. We'll set the instance variable that pops it off the stack, and then it stores it in the instance that we were talking about earlier. Then we'll get the value, and that pushes it back onto the stack, and then we call the puts function, and that prints out the value 10. So if we were to look at the virtual machine, like let's say we rewrote the virtual machine in Ruby, the instructions would look something like this. So we have a set ivar instruction and a get ivar instruction. So set ivar, all it does is it pops the value off the stack. It takes a name as the parameter. That's our instance variable name. It pops the value off of the stack and then stores the key and value, the name and the value. And then get, all we do is we find that value and we push it back onto the stack, given the name. So let's talk about some interesting properties of instruction sequences. Instructions live for the life of your program. So when your program gets compiled into these instruction sequences, those sequences live until your program ends. And another interesting property of instruction sequences is that today we're all virtual machine developers. So when I say we, I mean us as virtual machine developers. We can put anything in those instruction sequences that we want. It's not limited to anything. We can add anything we want to it. These sequences are private. We don't expose them to developers, so they can't see what's inside, so we can really do any kind of manipulations that we would like to do. So again, since we can store anything inside of these instruction sequences, let's store a cache. So in this example, we have our instance variables, and our instruction sequences have a name and a parameter. Let's add another parameter to the instruction that's a cache value. Something like this. So we'll create our own object that's a cache, and we can store these values inside of the cache. And since these instructions live for the life of the program, the cache also lives for the life of the program. So to drive that point home, I've kind of rewritten the instructions here. So like as a regular Ruby program. Uh-oh. Bye. So we'll create the instructions, and then we'll just have the virtual machine execute those instructions, and it reuses these cache objects each time. So we can say, okay, let's fix our get ivar instruction sequence. This is inside of our fake virtual machine. We'll say, okay, if we have an index stored inside of the cache, then we know it's a cache hit, and we'll use that index. Otherwise, we calculate a new index for that, store it into the cache, and then next time we'll reuse that index. So those indexes get stored inside of that cache that's stored inside of the instruction sequences. So it's a very roundabout way, but what this means is that each time we execute that instruction, we don't have to look up, we don't have to do that hash lookup every time. We do the hash lookup once, and then every subsequent execution, it doesn't do the hash lookup again. Any questions? No, okay. I can't prove, like, that one I can't prove to you with Ruby code. You just have to believe me. It's what happens. All right, so these are called inline caches. And we use them for things like method calls. So method calls use inline caches. When we, why wouldn't you use the inline cache with a simpler arrayless implementation?
Like the one you started out and said, hey, this is slow. Is there some reason that you can't?
So why would we do it? So we have to use the name somehow. The name is what gets stored in the instruction sequences. So let's go back to the example here. The only information, as the program executes, you'll see the set ivar and the get ivar. The only information that we have in that case is the name of the instruction. It's not an index to it. So we have to look up that index at some point. So the first time we'll look up the index with that string, and then the next time we'll use the same index. The reason that we do this is because I think the reason is because I know the reason. We don't know what instance variables will exist at compile time. So when the program gets compiled is when we generate these instructions. But we can't know what instructions, or we can't know what instance variables exist at compile time. For example, you could do something like, I don't know, like, I mean, don't do this. Right, we could set random instance variables. Please don't do this. But this is an example. Like the compiler can't know what instance variables you have set. So unfortunately, we have to use a combination of hash and index. Yes, you're welcome. Thank you for the question. I didn't think to explain that, and I'm glad you brought it up. Okay, so we use inline caches for these indices for instance variables. We also use them to look up methods, like where does the method exist before we call it. And we also use them for constant lookups. So whenever we have to look up a constant, like your user model or whatever, it'll cache the location of that constant in those inline caches as well. So to summarize, instance variables use an array and a hash for speed, not just a hash. We have to realloc on array expansions, but that's not true anymore in Ruby 2.8. Ruby 2.8 will not do a realloc, but older versions will. Cache lookups happen on inline caches. And please don't at me. Actually, I'm just kidding. At me all you want to. I love talking about this stuff, so please at me. Does anyone have any questions or anything you want? We don't have to talk about this either. We can talk about random projects I'm working on, or my job, or anything. Oh, thank you.
Hey.
You're welcome. You're welcome.
That was good, Aaron. Quick question.
Yeah.
Is there a difference on the hash array stuff for eval versus instance variable set? Or is it just eval is basically doing instance variable set under the covers?
It's doing instance variable set under the covers. It's all the same.
Okay. Thanks.
Yeah, you're welcome. I can show you the patch that I wrote that makes it the same. Like this is the longest. This is literally like. Let's look at the patch. Oh. Unless do we have any questions? I can't tell if anyone has hands raised. So if you have a question, either say it or type in the chat, and I have the chat open.
The hand isn't very clear, so definitely just chat or button.
Oh.
Okay, it's this one right here. This is the longest presentation I've ever given about a one-line change.
I also gave a very long presentation about a single bit change.
So let's take a look at the actual Ruby implementation. It's a bunch of C code, but now that since we've actually gone through and discussed how these things work, like maybe it'll make a little bit more sense. Let's do this. Let's check out Is that the branch name? Ruby 2.7. Okay. Looking for this thing. No. Here we go. Okay. So this function right here, this is the actual function that does the expansion of the array. Yes, there is a maximum number of instance variables you can have. Yes. So this is the thing that actually does the expansion. And it figures out like, okay, if there's how many, this num entries here, you see this one I have highlighted in yellow, this iv index table, arrow num entries, that's the hash table that contains the map of name to index. So we're saying, okay, if that number of entries is less than the size that we want, the new size, so we calculate a new size here. It increases by 1.25. So it doesn't double each, is that right? It doubles each time? It increases by 1.25. So we say like, okay, let's calculate a ratio here. We're not going to increase by 1, we'll increase by some amount. And this new size, if we want that new size, if it's less than the number of entries, then we'll just return the number of entries. Otherwise, we're going to return that larger size. And that's why we see on the very first allocation, we'll see it's larger than the table. And on the next one, it's actually clamped down to the table size. So all I did was go in and like remove this and this. And now it's actually much less complicated. And I probably shouldn't have given you this presentation.
How long? Thanks, Aaron.
Yeah, you're welcome.
No, but seriously, thank you so much. Like I love stuff like this. Like I love doing kind of like deep dive things like this. It gives me a lot of context for the way that Ruby works, but also just like, I don't know, we all build software on a lot of stuff that has existed for decades that we don't necessarily understand all the time. So I really do appreciate stuff like this where I can like say, oh, okay.
I'm glad, I'm happy to give a presentation, and I really like, so I actually really enjoyed doing, where did I put that script? What did we name it? B.RB?
Mm-hmm.
Well, it was not here. So, oh geez.
That looks different.
Is it here? Ah, there's the right one.
That other program is way too complicated for me.
Please don't look at my file system.
I know a developer named Tim who names all of his files Tim1 or Tim2 or Tim3. So.
Is it Tim Terrell?
No.
Oh,
Would not
McKinsey.
surprise me.
Jason knows who I'm talking about.
If it's an output file, it's tim.out.
Every time I do debugging, I'll do like puts hi mom, because like I hope that someday my mom sees it and is like, oh.
It's awesome.
Aaron said hi. Yeah.
So I do this thing all the time, and it always gets caught on code review where I'm like, I'll get a ticket that comes in. It's like a bug report or something. And I'm like, okay, well, I need to investigate. I don't know what's going on here, but I know like roughly. So I will make a test at the top of the file that just says, it lets me try some stuff with a binding.pry in it. And then they're like, okay, well, I'm gonna like post against this endpoint and like try some stuff out and put a bunch of prize through. But then eventually I end up writing the correct test where it belongs, like in the test suite. And I'll forget that I had this giant, like this thing at the top of the file that was like, hey, it's just me playing around. I'm sorry. I do it all the time, like all the time. I get called out. I was like, hey, this is a great diff, but why does this test exist?
What is this?
And it's always like, oh yeah, I was just playing around. I'm sorry.
Elise, it sounds like you need to write a Rubocop that catches your bad habit.
I should do that. That's a good point.
Take Aaron's practice of saying hi mom in there and then have a Rubocop that looks for hi mom. There's your hack.
So this is exactly what like get push -f is for. Like I didn't do that. I don't know what you're talking about.
Well, the thing that is really embarrassing is that at my last well, not my last company, but at one of my former companies, like what would happen is like no one would ever call me out on it. They would just send me PRs. It's like, hey, like you left this thing in here. You left this test that all it has is a pry in it. Like, can you delete it? I'm like, yeah, sure. I approve, merge, whatever. You know.
That's funny. What else can I show you? That was one line. All this for one line.
I have a funny question. I have a funny question for you, Aaron, because you love cats like I do.
Yeah.
What are your thoughts on the Tiger King?
Oh God. Well, I mean, I have a lot of thoughts on the Tiger King. Like, first, I have a lot of thoughts on the Tiger King. It's awful. It's an awful show. The whole thing. I mean, it's really good. Like, it's a really good show, but the entire like premise and everything in it is just not good. It's good TV, but it's good TV that should not have ever been made. How's that?
Yeah, that's good. That's good. I ask every person like way into cats that question.
It's sad, like to me. So it's very good TV, but it's sad that it's a TV show that exists. If that makes sense.
I'd agree.
Right now. I'm watching Money Heist. Has anyone seen that? No. It's on Netflix. It's super good. It's really good. Like it's about like I don't know these like Spanish gangsters. Not gangsters. They're like just they're bank robbers, and they go rob the Bank of Spain. But like somehow they make this robbery last for the same robbery. It seems like this robbery is lasting for 4 seasons. It's like wow. It's the same robbery. It's lasting 4 seasons, but it's like it's so gripping that I'm like, oh yeah, I'll watch 4 seasons of a robbery. Yes.
So I've been rewatching Lost recently because like I actually like Lost. I'm sorry, I know a lot of people don't, so I apologize if anybody's like Lost the worst show ever. But that's
tell us about season 6.
Season 6 is actually great, except for the fact that they like tease killing Kate like every episode for no fucking reason. But no, actually, so this is really interesting. So I've watched prior to right now, like I'm watching it right now, but prior to right now, I've watched it twice. I watched it when it aired, and I watched it once after that. And the thing that I'm struck by watching it now is that it's like the perfect show for the moment that we're in. Because the whole theme of the show, like in the 5th episode of the entire series, Jack stands on a beach and says, if we can't live together, we're going to die alone. And that becomes a meme throughout the entire show. It's like live together, die alone is brought up every time they have to deal with all this bullshit, like anything they have to deal with. And the show is really about like coming together as people to to like build something better than where you're at, right? Like they're in a plane crash, and to build this, they have to learn to be a community together. And it's really interesting to me because like I love the show. Like I loved it when I first watched it, but I love it now for that aspect of it, where it's like all these people are learning to work together in the midst of a tragedy. And like I'm only a couple seasons in on this like watch, but that's really what the show is about. Like if you ignore like not even ignore, like I think that every other theme plays into that theme, that like it's about people should come together, and it's about the way that we come together and how we deal with each other and how we build communities or whatever. And yeah, so I've been enjoying it, but it is also like, a lot of people don't like that show.
I thought it was a great show. I loved it until it, like I was kind of disappointed at the end of the show, but the way the rest of the show I thought was amazing.
Yeah. So what's really funny is I was disappointed with the ending of the show when I first saw it. And then I watched it a second time and I was like, this ending makes perfect sense thematically. Like it's the only ending you could expect thematically, because the theme of the show is like the whole show is about finding a community. Like in the final episode when Christian says, what's it he says? Like you all needed each other. They needed you and you needed them. The whole point of the show is that no one, like you can't possibly live life by yourself. That's the whole point of the show. And everything sort of fits together when you like approach it that way.
I'm gonna butt in that Paul has a question.
Ooh, Paul has a question.
Oh, let's see.
It's fine. The lost discussion is fun.
Yeah.
So the question is, it looks like it was originally added as a, yes. It looks like it might have been originally added as an optimization. Did something change that it was no longer needed, or was just never benchmarked? So I don't think that it was ever benchmarked, but on the other hand, like actually I developed this patch while I was working at GitHub, and we tested against our code. This patch works well if you have classes that don't instantiate all of their instance variables. So if they're only partially instantiated. But we found that, like, we ran against our code at work, and we found that the vast majority of objects actually use up most, if not all, of their slots. So what ends up happening is they expand all the way to the maximum anyway. And because they do that, like, there's no point in doing this incremental growth. Does that make sense?
Yeah, trying to think of how to word a follow-up question. Like if a class has, like 4 instance variables, yeah, well, you showed it where it had 2 and it didn't change size. And then you added 3 and 4. And so whatever limit, 8, where it would then go allocate more. It seems like if most instance variables or most classes have, less than 8 instance variables, it'll allocate and reallocate once and then it's done. And so, instead of allocating the whole thing, yeah, you've saved that one realloc, whereas in your benchmark, it was reallocating what, 500 times? So that was obviously slow, but I don't know, I guess between the Rails router and the controller view namespace, there's probably a ton of instance variables that sit around unused most of the time.
I'm not sure. We just measured the objects that were allocated in our application, and basically what we did is we said, okay, we compared the, how did I do this? Now I'm trying to remember. Ugh. When the object died, I remember what we did. So we basically hacked the garbage collector so that when the object died, we could see what was the size of the array. and then compare the size of that array to the size of the IVAR table. And then we could see, based on that, what percentage of like objects that came to life and then died, what percentage of them actually filled out the entire IVAR table. And that happened to be all of them. Well, not all of them, but like 98% or some very high percentage. So it's true that there's some where that could be like wasted space or we're allocating too much, but the percentage is so small that the savings of reallocs is worth it.
I suspect it also plays well in a world where humans write code that leads towards God classes that have tons of IVARs. I mean, that's just how, like, unless you're really careful, you end up with some class at the center of the universe in your application, and it's got a ton of variables in it.
Yes. The other weird thing too is if you want to talk about like size. So we were showing I'm still sharing the code screen, aren't I? You can all see my code? Okay.
Yeah,
cool.
code.
Yeah.
Okay. So like, let's say we have some classes that only, well, how do I say this? So let's say you have a class that allocates some IVAR some of the time and other IVARs other times. They tend to converge, or the size of them tends to converge on the, the intersection of them, if that makes sense. So even if, like, let's say we have our example here that's A through Z, 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 right? And later on, some instances only allocate a few instance variables. It's extremely likely that those instance variables will be ones that cause it to realloc multiple times. So we still save. Though in some cases, it's true, it'll use more memory. It's absolutely possible. Oh, thank you. I enjoyed writing the foreword in Ruby Under a Microscope. That was a good book. I've always thought about writing a book, but I don't know what I would write it about. And also I don't have the patience, I don't think. I really enjoy it. Like, I enjoy talking to people a lot more than like writing stuff. Like, actually writing slides is extremely stressful for me. I don't like doing it. But I like giving presentations and teaching people things, so I can, like, that's enough to like get over it. You know what I mean? If I wrote a book, it would be just like writing a whole bunch of slides, and then I never got to do the fun part.
Everybody I know who's written a book says, don't write a book.
I think I tweeted once, I'm thinking about writing a book, and then I got like hundreds of replies that were like, don't do it. Just don't do it.
I mean, I think there's a uniqueness perspective, right? Like I've never wanted to write a book because I just feel like, what would I say that hasn't already been said? Like, it's like I feel like it's pointless for me to write a book because what is added to the world that, like, all of my opinions are drawn from other people's stuff that they've already published. That's like, okay, well, my opinions are everybody else's opinions, and there's tons of books that do that. So, I mean, the money, that's the reason.
Because authors make so much money.
No one writes software books for money, at least. Let's just set the record straight.
Yeah.
No, they make Twitch channels. That's how they make money.
I don't think so I don't think you don't have anything to say. Like, so all the stuff that I've given to you in my presentation today is like it's not my ideas.
Okay. So here's what I would say is that it's not, maybe I misspoke. It's not that I don't think that I have anything to say. It's more that I think that I don't have anything to write in a book. Like, I have a lot of stuff to say, but I think the format for what I would want to say is not writing 400 pages in a book. like a lot of, especially for engineering and for business, which like the books that I read in engineering and business, I read like 100 to 200 pages of a 500-page book, and I'm like, I get it, I know what you're saying, and I throw it up, and I'm just like, I'm done, bye, you know, like,
See you then.
oh, bye, Dan.
Yeah, I think that's why blog posts are popular, although they can sometimes not dive quite deep enough. To sort of sum up, given that we're getting close to the end, Aaron, what side projects and what are you doing at Shopify? Like, what's that kind of your life there?
So I'll talk about side project. Well, I guess it doesn't matter. I'll talk about work first. So I recently started a job at Shopify. I am on a research team, and we're just doing like essentially R&D work. My job is mostly like working on Ruby. So I'm doing right now I'm looking at GC stuff. I'm working on making the compact. So Ruby 2.7 comes with a compactor that I wrote, and I'm working on in Ruby 2.8 making the compactor automatic. In Ruby 2.7 it's manual. You have to say like gc.compact, and then it does its thing. I want it so that you don't need to write that at all. It just does it automatically. So I'm working on that. But I'm also going to be working on, like, there's a whole myriad of other projects that I'm going to be working on. As far as side projects are concerned, like, I've been getting into electronics a lot lately. Like, I've been learning how to do circuit board design. Like I started doing, before I dropped out of college, I was a computer engineering major. So I did a lot of electronics stuff, and I'm starting to pick that stuff up again. And I'm going to show you, this is my very first, well, it's not my first PCB. This is a PCB that I made. It's one of my few.
How do we stop you from sharing your screen and make the screen bigger?
Oh, I'm sorry. I can do that.
Yeah. That looked really sweet. There you go. Now you're huge.
Okay.
So that is the B again?
Yeah. So here's one of them. This is my first like surface mount PCBs that I did.
Yeah.
Actually, let me find the very first one I made. So this is the very first PCB I made. And let me do the YouTube thing. Okay, this is like, so when I say made, I didn't make it. I designed it, and then I shipped the design. I shipped the design off to a manufacturing company, and they made it for me. But what it is I wanted to measure actually, I'll show you the thing I built. So this is the thing I was building. Here it is from the side. This is the back. And what it is it just measures temperature, humidity, and essentially like PM 2.5, which is just fine dust particles. Basically, it's the size of particles that'll cause cancer, essentially. So I wanted to build one of those. And yeah, so I was learning how to make PCBs. And what I did, like, I was extremely intimidated, but I found the YouTube channel for DigiKey, and they walked like through the entire process.
Awesome.
And then like I followed their guides on YouTube and their tutorials. And after I did that, I was like, this is much easier than I thought it would be. Like I was very afraid, and then it turned out to be way easier than I thought. And then I shipped it off to I found a manufacturer. Like So there's a manufacturer called JLC PCB, and they'll make your first PCB for like $2, including shipping. So my very first one cost me like $2, and I was like, well, you know, if I mess it up, it's like it's $2, right? It's fine. So just did it, and it seemed to work out. So now I've been making a lot more, and I'm like spending way too much money on this hobby. As hobbies go. Oh, and speaking of spending too much money on hobbies, I'm also doing cheese making.
Yeah.
Oh, and speaking of spending too much money on hobbies, I also am building keyboards.
Yeah.
Oh, okay. So this one, I want to ask you a question.
Check this out.
Let's
Whoa.
okay. So
I'm halfway. Sorry.
here's like I bought this. This is a SA Sakura with Cherry MX clears. You can't see it because I'm doing this background and I don't have a green screen, so whatever.
I can see it.
But one of the big things that I've been looking for is like I want to build like this one I bought, but I want to actually get into building keyboards. Like I want to build my own, and I want to build my own primarily because I want to I just want a nice tactile silent switch. Like I hate the MacBook keyboard. Well, I guess they've just gotten rid of the shitty butterfly keyboard. But my question is like, where should I start if I want to build my own keyboard? I'm sorry, your face looks like I just asked you like the worst question ever. I'm sorry. I'm so sorry.
No, I don't know. I don't actually know. Like,
there's a bunch of suppliers that source like all the parts, and you'll have your board, your tray, your switches, and your case, and it's just Legos. You just put it together and then just solder the pins.
yeah, it depends. Like, if you want to do, so you can buy kits where they've like already designed the keyboard, like the layout of the keyboard, and then you can buy pick the switches and stuff that you want. That's probably like the easiest way to start. If you really want to like completely design it yourself, like layout and all that stuff, like I'm not even there yet. You have to design your own PCB and do all these different things. So like,
I mean, I guess my question is like for somebody who wants to build like their first custom keyboard. So like maybe like for me, I think what I would be looking at is like a 10 keyless or like a 70%. I don't. Yeah, 70%. Is it the one without the? Yeah, it's like a 10 keyless or 70%. So like if I could get something that's like a kit would be great, to be honest, where it's just like, oh, I can learn I get a kit and I can learn how these things work and how all this stuff works together. I have basic soldering skills, so I'm sure I could solder it, but like, I don't know. I guess, how do I get started?
I'm trying to think here. So there's good websites. So the problem for me is that I exclusively use ortholinear keyboards.
Oh God. I'm sorry. I didn't mean to ask you. I didn't know. If I knew, I would.
No, it's fine. It's fine. Like I've built at least like 10 keyboards at least, but none of them are the ones that you're looking for.
So can I actually ask you a question?
Sure.
I mean, I do still want the advice about where to start, but I am curious about why ortholinear. Like I asked this on Twitter a bunch of times and no one ever gave me an answer. Like, what is the deal with the ortholinear? Like, what's the benefit?
Hey, you gotta sum that up quick, and then we'll stop recording, and then I think.
Yep. So the benefit of the ortholinears is that if you look at the keys, you just move your fingers up and down. You don't move them like in a diagonal fashion. So that's basically what it's supposed to be. So it's less, not as hard on your hands, supposedly.
Yeah, it's a more natural.
Okay. All right. Cool.
This is one of the ones I've built.
Wow.
Oh, cool.
That's awesome. Yeah, I think that was a really cool conversation to keep going with. I just wanted to sort of say we're at sort of time, and Aaron had given us a gazillion amounts of your time.
Yeah.
And I think we could all talk and listen to you talk about things for hours. So you're definitely welcome back anytime that you would like. And I think you did very well, and you don't need to be nervous about kind of giving this kind of presentation. I think we
Thank you.
made it work really well. And all the feedback I've seen has been really positive about kind of your acceptance of like, hey, let's type this, let's try that, which I think makes a really cool interactive and different sort of take than an in-person or even a conference talk. So I just want to say
I have to say, like, this is a whole lot of fun. This is the first time I've given a presentation on like doing like this. And it was a ton of fun. I'm glad we did it. Like, I'm glad we made it interactive. It was a good, like, I had a good time. So thank you so much for having me.
Yeah, we're super happy to have you. I think everybody was pretty blown away by what they learned and just diving into those kind of fundamentals of how things work.
I think there's a specific piece that I really appreciated seeing is as you're diving into like the depths of Ruby internals, and most of us who are writing Ruby have some other thing on our mind about the business software we're writing. And it turns out you're doing the same thing in the Ruby internals that we're doing in the business problem. It's just sort of manipulating a different bucket of bids. But it's super helpful, I think, for folks who are across the industry to get a sense that we're all really doing something very similar. Take the mystery out of the whatever parts we think are outside of our expertise and say, no, there's just some person working hard on a stupid little problem that creates bugs and does strange things. So that's the piece that makes me especially enjoy that content and talk and so on. Thank you.
That reminds me
Thank
of
you.
expert is someone just muddling around with a
Totally.
Yeah. Actually, Eric, that's an incredibly good point, because one of the things that I've been thinking about a lot recently is just like how building software for businesses is like, it's like self-similar on different scales. Like you just, like the business has an idea and that idea distills into software, but like maybe you don't understand that idea. And so all you get is what they're asking for requirements, and like how empowering it is to know what they want, what they're actually trying to do, right? And yeah, that's very interesting. It's a very interesting analogy, because like it does matter on some lower scale that maybe you're not paying attention to.
Well, I'm going to cut.
Thanks.
So I can stop just so that we don't keep people coming.
Yep.
Again, thank you, Aaron.
Yeah, thank you so much. I am going to start my second job now, which is playing Animal Crossing.
It's awesome. Awesome.
Enjoy that.
Cheers.
Yeah.
Thanks
Great,
again,
thank you.
Bye, everybody.
Bye.
Appreciate it.